Okay. First of all, I would like to thank organizers for inviting me to give a talk in what promises to be a very exciting symposium. And obviously, Martin and organizers saw things that cryo-EM becoming too easy. So they decided to make this symposium so that it's more difficult to follow. You will have to be confused. And that's just a selection of topics look like no selection of topics. All the of topics looks like a bit random. And that is just, you should not be confused and should understand that cryo-EM was like that before. Now it is not like, it's not like that. So our work comes at the end. At the end, when you have maps, you have coordinates, then we can help you. Otherwise, you have to go ask something, George or somebody else to help you. So I'll talk about a refinement of atomic models against cryo-EM maps. And here's the contents, and I'll tell a little bit about REFMAC, and then fit into cryo-EM maps, and then something about structure-based restraints, and then a composite map refinement, something about overfitting, and a little bit about effect of over-sharpening. And since the field is very young and people are trying, everybody is trying to push the boundaries as far as possible. Sometimes the boundaries, there's nothing to push for further. And sometimes people claim higher resolution, and sometimes people use tools that are not suitable for cryo-EM refinement and cryo-EM refinement and map calculations. And I should tell you that from my point of view, refinement against cryo-EM maps is a young field, and it is still developing, and there will be more development in future. And here I will give some of the tools that can be used within REFMAC that can be used to fit atomic models into high resolution EM maps. And at the moment, so far we are using all these tools using scripts. And I think that with CCP-EM, these things will become easier. Hopefully, in future, in 1 year time, you will have to push a few buttons instead of running scripts. But at the moment, if you want to use different tools, different options in the programs, you will have to use at least some bash scripts. Okay. REFMAC is just one of the programs for refinement of atomic models, and it was originally designed for macromolecular crystallography. It was not designed for cryo-EM maps. A few years ago, when high-resolution maps became available, we had to adapt our programs to make it suitable for EM maps. It is based on some elements of Bayesian statistics, and it tries to fit chemical and structurally sensible models into the maps. By definition, it uses two components. One of them is that the information about the structure, and another one is that how current structure is fit into the maps. That is it. That's basically what's Bayesian statistics. In spite of all these complications, you should not be confused by the names. Name or terms are there just to confuse people and to make us to look cleverer. In fact, all these things are much simpler than you think. REFMAC can be used to fit atomic models into cryo-EM maps, and it can do some map manipulation, sharpening, blurring, and at the end I'll tell a bit about that. Basically, what is refinement? Refinement is that you have an atomic model, refinement of atomic models. You have an atomic model, and you fit into the map, and you make sure that fit is as optimal as possible. At the same time, structure is as structural and chemical sensible as possible. In crystallography, we also use we calculate difference maps. At the moment, in cryo-EM maps, fitting against cryo-EM maps, we do not use so-called difference maps and updated maps. So you have to always consult original observed maps. To do this fit, we have to use first of all properties of the data, and second we have to use as much information as possible about the structures, proteins, nucleic acids, and so on. And fit into the map is done using so-called like root function, and in cryo-EM map the like root function for individual components look like that. There's nothing complicated. It's just if you take logarithm, it is just least fitting. And there's only two more components. That one of them is that how well map describes the model. Or model describes map describes the model, and second is that what is the error in the map. At the moment, that component is not used, so that component, the error in the data or error in the map, that is one way of ensuring that a model is not overfitted into the data. That describes the noise. If you do not have that component, then model will be fit not only into the signal, it will be fit into the noise also. That is the definition of overfitting. Major differences from crystallography is that variance of noise is large at high resolution. And in crystallography, we do not observe phases. In EM, phases are available, and it's claimed that phases are even more reliable than structure factors. At least in one paper, somebody claims that amplitudes are more reliable, but analysis shows that it is not so. So phases are phases and amplitudes should be considered together. They cannot be considered as two different components. That's basically what is the fit of the model into the map. So since EM maps do not have very high resolution, they are medium and at medium resolution. I think highest resolution in spite of claims that it's at 2.2, highest resolution is around 2.5, 2.6. So we need to use some information about the structure, about macromolecules. What do we know about macromolecules? We know that if macromolecules, they are chemical compounds. By definition, if they are chemical compounds, they consist of atoms. Atoms are bonded to each other, so we can use that information to stabilize refinement. Second, we know that if there are two molecules with sufficiently high sequence identity, it is very likely that those two molecules are similar to each other. It means that if there's a available structure in the PDB that is similar in sequence to what we are refining, then we can use that information to stabilize refinement. And then it is highly likely that if there are two copies of the same molecule, then they will be similar to each other, at least locally. There may be conformational changes, but molecules will be similar to each other, at least locally. And we can say that if two atoms are very close to each other, then oscillation of one and oscillation of both of them should be very similar to each other. It is just what is called a B-value restraints. And proteins tend to form secondary structures, and DNA, RNA tend to form base pairs. Stacked base tend to be parallel to each other. So these are basic information we know about macromolecules, so we can use them to stabilize a fit into the map. And one of those tools is just using restraints to reference structures. And that restraints to reference structures is done using one of the programs written in our group by Rob Nichols. It is called ProSmart. But if you are defining one structure and you have something similar in the PDB, And something similar in the PDB. What does it do? That it takes the structure from the PDB and then aligns them using structures. It doesn't use sequences. It uses a structure-based alignment. And then once they are aligned, then finds the corresponding atoms and says that the interatomic distances between corresponding atoms must be similar to each other. What does that mean? It means that then local conformational information is transferred from high resolution to low resolution. I hope it makes sense. And then it can be done for proteins as well as for nucleic acids. And these restraints are generated using ProSmart, and it can be visualized in COOT. And here, for example, we have a target structure we want to refine in yellow, and in purple we have a structure that we think that is similar to what we want to try, what we try to refine. So then interatomic distances, non-bonding interatomic distances from a reference structure is taken and mapped to target structure we are trying to refine. And at the end, what will happen is that interatomic distances, in this particular case, between nitrogen and oxygen, will be similar to between nitrogen and oxygen from the reference structures. It means that locally these structures will be similar. If you use this type of restraints, you may have a global conformational changes. However, locally structures will be similar. I hope it makes sense. So another information I said that we can use is that secondary structures. We know that proteins tend to form alpha helices, beta strands, and alpha helices, beta strands have a certain patterns, and those patterns could be mapped to our structure, and to make sure that what we refine at the end will have a secondary structure element as we expect. And another information that's used for stabilization of refinement is so-called jelly body refinement. All these tools are used because we do not have enough data. If we would have enough data, then we would use only data to fit our models into the map. If we would have 1 angstrom EM maps, at some point probably you will have, but not now, not today. And then you could just say you don't need any extra information. You could see each atom independently, but it's not possible. So we have a limited amount of data. Limited amount of data means that many different models can describe exactly same data, and but not all models are real, and some of the models may be complete nonsense. And to select among many models that describes our model as well as possible, we use this extra information. Reference structure restraints and secondary structure restraints. They are designed to select among many models the best possible models that is structurally sensible and that can give us some information. And one of the tools we use is so-called jelly body refinement. What does that mean? That jelly body refinement. You have let's say that you have a model you want to fit into your map or crystallographic data, and let's assume that starting conformation is correct, but there may be conformational changes. The starting local conformations are correct. So what we say is that since starting local conformations are correct, then we try starting local conformation to keep starting local conformations as intact as possible. And what does that mean? That in terms of mathematics or in terms of chemistry, how can you describe local conformation? Local conformation can be described by pairwise interatomic distances. And what we do is that we try to keep pairwise interatomic distances as close as possible to starting conformation. But at the end, what happens that atoms move atoms close to each other, they move in concerted fashion. If they move in concerted fashion, it means that you can have a flow of molecules. But local conformations will be kept intact. Here's an example that is at 10 angstrom. I think it is unlikely that you will ever, or at least in nearest 5-10 years, you will have at least at 10 angstrom EM maps for such small molecules. But I've taken that from Myotop's that data set from Myotop's paper, and the map is at 10 angstrom. We have a starting molecule in gray, and after jelly body refinement, after 150 cycles, secondary structures move in concerted fashion into the map. Now you can imagine that if you take all interatomic distances and to keep them intact, then how can the molecule move? Only way molecule can move is rotate and translate. Okay, and it means that at the end, in the limit, it becomes rigid body refinement. If you take only very local information corresponding, let's say, secondary structure elements, let's say 4.2 angstrom is the default value. Then secondary structure elements will move together, but there will be a conformational movements. If you look at that, for example, that helix moves into here in concerted fashion, and that loop moves into here in concerted fashion. This way, this technique assumes that starting conformation is sufficiently correct. If starting conformation is not correct, then this type of tools may not work as well as you would like, because the tool tries to keep starting conformations intact. Okay. So when you build model, you should make sure that conformation is as correct as possible. Then you can use this technique. Otherwise, this technique cannot be used. And another tool that is these tools I described so far are mostly for all structures. For proteins and as well as nucleic acids, and here there are a few more tools that are specifically designed for nucleic acids, and these tools are Basepair restraints and parallel plane restraints. Basepair restraints says that if there are two bases that are close to each other, then it's very likely that there will be a hydrogen bond between them. But there's a hydrogen bond between them, but there may be rotation or there may be buckling. And this kind of information are encoded in Basepair restraints. And if there are two bases, and then it's very likely the bases. Then it's very likely that they are parallel to each other. Not only two bases. Let's say that you may have one base from nucleic acids and a phenylalanine, and it's very likely that these two aromatic rings will be parallel to each other. And these tools were used for refinement of ribosome structures. And here's a flow chart. I will not go. I will not stay on this slide too much, but I'll tell a few things that REFMAC can be used. REFMAC is used for that. Input can be multiple composite maps, and I'll tell about that a little bit later. What do we mean by composite map? And you can add the external restraint structures. You can also use electron scattering factors, and I'll tell a bit about that in the next slide. And you can, if you have a symmetry, then you can use symmetry restraints also. In principle, if you think about electrons and X-rays, X-rays are photons, and photons interact with electrons. So what you see at the end is a electron density. electrons are negatively charged. They interact with electrons as well as with nuclei. So what you see is electrostatic potential. So what is the relationship between electrostatic potential and electron density? Is that a so-called there's a Poisson equation, and Poisson equation that relates these two entities. And solution of Poisson entities was derived in 1930s by Mott and Bethe, and it says it relates X-ray form factors with electron form factors. X-ray form factors with electron form factors. And when S is a vector in Fourier space. When S goes to 0, then Fxs is a number of electrons in an atom. And if the number of atoms, number of electrons in an atom is not equal to, and Z is a number of protons in a nuclei. If number of electrons is not equal to number of electrons is not equal to number of protons in nuclei, in other words, if an atom is charged, then that entity will go to infinity. What it means that in practical sense that that entity will go infinity. That's one side of that. But in practical terms, it means that at large resolution you would have very big peaks, and it would mean that in principle observing electron diffraction would not be that easy. That's one side. Another side is that as S goes to infinity, it becomes large, and electrons depend on number of points in a proton, and it goes it moves very slowly. And in image space, what does that mean in image space? In molecular space, it means that effect of charges would go as Coulombic interactions, and it would affect effect would be extremely large, and at very long distances. In crystallography, it would mean that it would be impossible to observe crystallographic data, which is not true. We know that it's possible. We observe that, and in EM, it would mean that the molecules would affect each other, and you would not observe. Observations would be extremely difficult, and they would be electrostatic potential would be very flat, but it is not like that. And the reason for why it is not like that is that there is a so-called molecules and charges are always in a solvent. And it is they are in a solvent. It means that if they are in solvent, negative charges will be screened by positive charges, and they will cancel each other out, and then they effect a long-range effect will be diminishing. So that's why we observe, and that's called a Yukawa potential. It could be used like that. And in the REFMAC, we have implemented that, but in for total structure factors, and total structure factors, it looks like that. That one, it looks like that, but it doesn't account at the moment for charges, and it doesn't account for solvent. And to account for solvent, you need to update. You need to change only one of the terms, and that is going to be done in future. That's about electron form factors, and REFMAC can use that as an electron form factors, as well as a tabulated form factors for electrons. But tabulated form factors for electrons use Gaussian approximation, which is not valid for for electron diffraction, because electron diffracted from electrostatic potentials. Now, here's an example of reference restraints to reference structures. You have a structure you want to refine, and you have a structure that is similar to your structure. Then you try to make in places where they are similar, as they should be similar, you try to make these structures similar. And at the end, you get something more sensible. Here, you don't have any beta strands, for example. Here, at the end, you get a much better structure. And reference, this type of restraints can be tuned to local resolution. As you know, that in cryo-EM maps, you get various resolution at different places, but it's a completely different matter. We will not go into that. These reference structures can be tuned using information about local resolution. For example, where you have not a high resolution, you could use a much tighter restraints because when you have less data, then you have to use more information from somewhere else. When you have more data, and then you could use less information from somewhere else. And what is the resolution? In fact, resolution is just directly related to signal-to-noise ratio, and resolution is related to how much information, how much data you have in the map about your model. If resolution is low, it means that the amount of data is small. So you should use some information from somewhere else, and somewhere else is just a structural restraints for using reference structures or secondary structures, or jelly body restraints, or Basepair restraints. There are many different choices, and I hope all these things will be available in CCP-EM so that you don't have to you don't have to write a scripts in future. But at the moment, you will have to use those scripts. So next point is a refinement against composite maps. It's very often, and one of the powers of cryo-EM in comparison with crystallography is that in the same sample you may have different conformations. And it's the same sample, you may have different conformation. If you, and George may talk about that a bit later, but I'll just tell that you may have different conformation. It is a good thing that it can give us some information about the structure. And if you have different conformations, what you could do is that they take different portions and they mask and reconstruct each portion separately. At the end, you may have for same structure, for example, for ribosome, you may have different reconstructions, and based on different masks, based on different orientation, and so on. And when you have that, and for each map, you may build a atomic model. And when you have for each map, you have an atomic model. Let's say that you have two portions, portion number 1 and portion number 2. For portion number 1, you have built an atomic model. For portion number 2, you have built atomic model. And then you can refine them separately, but at the end, you would like to refine those two molecules simultaneously, to get more or less right interface between those molecules. Obviously, this type of things can be done if you have discrete states. If you have continuous states, then it's very unlikely that you will be able to do this type of reconstructions and this type of model building. And second, that even if you do something like that, you should be very careful with in interpreting that interfaces, because implicit assumption in this type of reconstruction is that you have at least two states, and you reconstructed one and reconstructed another. If you have two states, it means that the interface is changing. Interface will be different for different conformational states. So, but that type of refinement, that type of analysis can give you some information, but you have to be careful in interpreting those information. They probably need to be dealt with separately. Next topic I'll just mention is that overfitting. No, overfitting is overfitting has the many different interpretation, and a main interpretation I like is that overfitting is that you increase the number of parameters so much that okay, I'll start rewind back. When you have a data, you have a signal and you have a noise, okay? And when you build a model, you would like to describe the signal, not the noise, okay? And since you have let's say that your signal would be like that. But when you observe, you will never have a observation on this, exactly on this line. There will be always noises, some noise around that line. And if you use only two parameters, then you will have some line like that. You can increase the number of parameters and describe almost every point in the data. But you increase the number of parameters, describe the data as well as possible, but you describe your data has a signal and noise. You describe the signal as well as noise. What you would like is that to describe signal and but not the noise. And how it comes in statistics, it is a very general problem. When you build a model, what's the purpose of model? You would like to have you build a model. You would like to predict something in future. Something, and if your model is overfitted into the noise, and your model will not have predictive power. And how can you increase the predictive power of the model? One of the tools in statistics is a use of so-called cross-validation. You divide data in 100 bits, and they refine against large portions, and then small portions are considered as a future observations. So you refine and then predict. You refine, predict, and calculate predicted error. In cryo-EM, it's not easy to do. It would mean that in principle, how it could be done. There are several ways of doing it accurately. One of them is that if refinement is done against raw images, then it can be done very easily. But however, it is not done at the moment. What we do is that we do reconstruction, and then we do fit into the reconstructed maps. So when we do reconstruction, what happens? What happens that if you think about reconstruction, what we have is the projections, and using projection slice theorem. What we do is reconstruct in a Fourier space, and we average planes from different projections. And at the end, we have points in Fourier space. They will be correlated with each other. So since they are correlated with each other, it means that tools like free reflections, free R factor that is used widely in crystallography cannot be used in fitting into cryo-EM maps. So how can we do that? So how can we deal with this problem? And currently, probably it's not the best way of dealing that. Currently it is dealt with using so-called half data reconstructions. So what you have your all particles, and you divide into two halves, and then reconstruct first part using first part, reconstruct using second part, and then you have your final map. And then you calculate FS and so on, and that is done by, for example, in Reliant and so on. Then you do model refinement against model build and refine against a total map. And then when you have done all these things, and your refinement parameters are already there, you take your model and shuffle a little bit. At the moment, 0.5 angstrom seems to be sufficiently good enough. And then refine against 1/2, and you have refined, and then you calculate FSC against map you have refined, and FSC against map you haven't refined. If there's no overfitting, that is that is you fit your model into the data, and that is your prediction. That gives you your prediction error. and that gives you your fit into the map. By increasing the number of parameters, you can make this FSC as best as possible. But you cannot improve this FSC too much, or you may even decrease this FSC, because if that model describes noise more than the signal, and the relationship between these two maps is only the common thing, hopefully, between these two maps is that the signal and noise are independent. So by calculating these two FSCs and comparing them, you can say that what is the prediction error, and by this way you can say that what is the if your model is overfit. To do these things, one of the things that we had to implement is that to sharpen map against reference map. So you have three maps. One of them is final map with a filtered map, and two maps are unfiltered maps. They have to be unfiltered. And then you take your final map and sharpen each half maps against your final filtered map. And then use those maps to do refinement. And if you look at if you look at these plots, and if these two plots, one of them is against half map, you have refined, another is against half map, you haven't refined. And if these two curves coincide with each other, then it's likely that the overfitting is not very big. If these curves diverge from each other, then it's very likely that those maps are it's likely that there's a overfitting. For example, in this case is more overfitted than that case. And in principle and in general, it is impossible to remove all overfitting errors. Overfitting is we are dealing with statistics, statistical problems. In statistics, you never can. It's impossible to remove overfitting. There will be some overfitting, but you would like to have as small as possible overfitting errors. Only way of removing overfitting is not doing anything. If you don't do anything, then you will have no overfitting. But it's not good. You don't want that. Okay, for monitoring fit into the density, we use the so-called average Fourier correlation and average Fourier correlation. The main idea is that when you use overall R factor, overall Fourier correlation, or something like that, and they are dependent on weight. And weights are, if you sharpen unsharpened maps, those weights will be different. And the weights may be implicit or explicit. When you do sharpening and unsharpening of any filtering, you add weights into your calculation of statistics. You don't say that I'm going to use weights, but they are there. And when you use overall statistics, and the overall statistics will depend on let's say sharpening and unsharpening. And we use to avoid this problem, we use a so-called average Fourier correlation. Essentially, it means that in each regression shell, you calculate Fourier correlation and then multiply by number of Fourier coefficients and then divide by total number. That's the way of doing monitoring the refinement. That we don't use R factors. R factors should not be used in fitting into cryo-EM maps. Average Fourier correlations, they are better indicators, not best but better indicators. Okay. And I think last year, probably this year is also, now I'm moving to another point. Last year, probably this year also, as I said, that there are a lot of people, or researchers, we all are researchers, we want to push the boundaries of the field. And sometimes we want to claim something very high resolution, something very beautiful maps, and so on, so on. So my map is fantastic, and so on. To do that, to do that, sometimes we sharpen, and when you sharpen your map, what does that mean then? You will have lots of tiny features, and lots of small features, short range features. And if you use a local resolution, let's say, local resolution calculation is nothing more than a fitting a local cosine and sine waves. If you over sharpen, local resolution will look higher than in reality they are. And another tool, which I don't demonstrate here, another tool that is used very often, that a so-called 2FO minus FC or FO minus FC2 maps, that is very that is common in crystallography calculation. We have to remember that in crystallography we do not have phases. Whole crystallography evolves around the recovering phase information. In EM, you are lucky you have phases. You do not have to recover that. Any recovering using model will add only bias. And in crystallography, we are trying to avoid model bias. If you use 2FO minus FC type of maps, you will add a bias into your map. And by adding bias into your map, you will make your map look better. So it should be at the moment, probably in future there will be tools to update maps. At the moment, you should not use 2FO minus FC type of maps. You should always consult your original map, probably filtered, but original map. But over sharpening is one of the things. Another thing that is as I said, that if you sharpen your map too much, then it will look like that you have a higher resolution. And one of the papers is described this type of over sharpened map. They don't mention, but I mention. This paper, I should tell you that this paper is very nice, this work is very nice, and map is very good. And I even should tell you that map is much better than it is described in the paper. You can see all side chains, you can see all ligands and so on. If you look at the map, by looking at the map, you see some features, you don't see some features. One way of looking at if you have over sharpened or not is calculating either power spectrum or average amplitude versus resolution. If you look at that, at the end there's a sharp drop. If you have a sharp drop, it means that it is over sharpened, and you have to consider that when you calculate map, you have a lot of Fourier coefficients you do not include, you do not use. And if you do not use, and there you have a sharp edge, it means that you will have a series termination effect. And bigger that drop, bigger is series termination effect. Series termination effect can obscure completely signals. And an example is here. That is a map taken from the PDB. And if you look at the map, there's no for this map. There's no feature whatsoever in this region. But you see a lot of tiny local features, and as if the resolution is very high. But if you sharpen it by b-value 60, and you immediately see that there's a nice chain going here. And after a few cycles of refinement, in crystallography, few is 10, and in cryo-EM, few is 100. That's just a order of magnitude difference between them. So, and by looking at these maps and a few other things, that we came to conclusions that in principle, when you do model building, you have to use multiple maps, sharpened at different levels. Because at some places you may need larger more severe sharpening, and other places you may need blurring. For example, if you may have a protein, one is, let's say, that a rigid, another one is moving. And if you use very highly sharpened maps, that you will lose completely the feature of this region. But if you do blurring, then you will see at least this molecule is somewhere here, not out of place. And using various levels of sharpening or blurring is a good thing, and we think that that should be used as a standard. And I asked Tom Byrne, and he was kind enough to implement it in CCP-EM, that you give your map, and then it calculates, and you give your blurring levels. You cannot see that. but it is there, and you give different blurring levels and different sharpening levels, and it calculates the Fourier coefficients and calculates for each of them average average amplitudes versus resolution. And from here you could immediately say that that is severe oversharpen, that is oversharpen, some features will be lost, and that probably that map is the best map at the moment. Sharpening should be done so that at least it looks like that the fall of F amplitude should go to 0 at the end. And that is again Tom Byrne's work, and it's in CCP-EM, and it will be available for all of you. And that is conclusions that now REFMAC is one of the programs the refinement against cryo-EM, and cross-validation is a problem, and the refinement against half-dated maps seems to work at the moment quite well. External reference structure restraints help to stabilize refinement against limited data. And jelly body refinement is useful when starting model is starting local conformation is correct. Otherwise, it may harm and your refinement may go nowhere. Over-sharpening can obscure features of the map, and multiple maps with different sharpening levels should be used for model building. Some of the features of the map are at the moment available for CCP-EM. And I hope there will be more maps available. I think that in future, when we can, we'll have a few more features that are using a noise level and so on. But I will not go into that. I have already 45 minutes. Acknowledgements and the people from LMB, and most of them are from my group. And Alan Brown is many slides are taken from Alan Brown. I would like to thank EM users in LMB, EM users in general, and especially those in LMB who are in graphics room. They just when we walk through graphics room, we see a fantastic maps, and George being busy with them. And I approach, I said, "What is that?" And they tell, and then we see things that that's a problem we can solve. Or we can help. Yes, people of CCP4, users of our programs, and thank you for your attention. And I'll finish here and wait for the question. Thank you.
Okay, any questions for Garib? I mean, maybe I'll.
Thanks. I've got a question about the test for over-refinement of the model. So you showed a slide where on the left-hand side we saw those two curves that were completely overlapping, and on the right-hand side they weren't, which was a sign of overfitting. So I was wondering if there's a case somewhere there in between, like which is not as clear. Is there like one value that we could somehow come up with that would give a more sort of objective estimate how much overfitting there is?
Yes, that is it is. At the moment, I cannot say you any number that should you should have likes that or likes that. Yes, I cannot give you that number. And at the moment, only I can say qualitatively that those curves should be as close as possible to each other. Obviously, closest they can come, yes, they can coincide. Yes, but if they coincide, obviously you may not refine at all. Yes, and then you will have they will coincide. But you would like your model to be in the map. That's why you have to define against total map first, and to make sure that your model is in the map. Yes, and then do randomization. Yes, and then just look at these curves. That will give you a degree of overfitting. And there are if your model is in the map, then the only way you can have overfitting is that p-values. P-values increases the number of parameters, yes, and then you may change, let's say, the way you restrain your p-values. And okay, I'm sorry that I didn't answer to your question directly, but it is I would say that it is at the moment open question. Okay.
So, okay. Ali?
I just got a quick question. I was wondering, you're splitting the data in half there, so you're refining half the data to make a model and keeping half of it to test. And we're running out of data normally, so do you know if it would be better maybe to make a map from 3/4 of the data and just keep a quarter as the statistical test, or is there proof that it's optimal?
Okay. My view is that the tool that I would recommend is not available yet, even on paper. Okay? That is a refinement against the raw images. Yes? Then what you can do is that when you have everything fine done, yes, you have a, let's say, n thousand particles. Yes? You take divide it 200, yes, and take 90%, refine against that, calculate prediction error, and so on, so on, so on. Yes? That would be the best way of doing that. We use half data because it was available. Okay? Because showed that it is one of the ways of reducing removing overfitting. Removing overfitting is impossible. Yes? It was available. Yes? If you would do tools are there. Yes? If you want to do a quarter of them, yes, take quarter of them. If you want to take 10%, take 10% of them. Yes? But the whole idea is that you refine against one part, yes, and then calculate a prediction error. But when doing that, if you do quarter or 10%, you have to understand, you have to remember one thing, that the noise level for 10% of particles, yes, will be much higher than noise level to 90% of particles. So when you calculate your prediction error, you have to factor in a noise level also. Okay?
Yeah, so would you give me a number? What's the best fraction to use?
Okay. She's waiting, I suppose, some time now.
Thanks. So I just had a question about your symmetry restraints that you said that you could implement.
It is there, yes.
So I mean, given my last talk, I've got molecules that are not symmetrically arranged, but I would know the transformation matrices between them. Is there a way to input that information in as well
yes,
now?
you can put transformation matrices. Yes, you can. You can, yes. You can put that, yes. But from your you can put transformation matrices. That is there. Yes, that is if you have PDB file. Yes, it has either biomatrix or a matrix or something like that. Yes, in PDB file, you can use that. There's a tool, and I'll send you that header to matrix. Yes, will extract and make useful for refinement. If you know Euler angles, yes, or polar angles, translations, you can use that. If you have matrices. Matrix and translation, you can use that. Yes, but in your case, what was interesting is that it's very likely that molecules are not completely same. Yes, it's very likely that there are some parts are same, some parts are not same. So what you would like is to restrain where they are same, not restrain where they are not same. For that, we have tools called local NCS. Yes, local NCS is based on local interatomic distances. Yes, but your resolution is 7.4. 7.4 is not bad. We have seen I wanted to say worse, not worse, but lower resolution. It's very, you can use that, but there are tools. Yes, you can give matrices, or if you have sequences, yes, then you don't have to give anything. Then you say that I want to use NCS, okay, and then program will calculate all matrices and all local similarities and so on. Yes, okay. Did I answer your question?
Yes. The question is that built in already to REFMAC 5, or do I need to use other CCP-4 programs to use local NCS restraints?
Everything is in REFMAC 5. Yes. In CCP-4 it is there. In CCP-EM it will be there. In REFMAC it is there. Last time I looked, it was there. Yes. And CCP-4, unfortunately CCP-4, for CCP-4 you need a reflection data. But for CCP-EM, is it there? No?
You can convert that from, you can get the reflection data from the map data.
Yeah, but what I mean that there's NCS. But can you add a keyword?
Yes.
Okay, you can use a CCP-EM, yes, and you give everything, and then I send you one line, and one line is sufficient to use a NCS. Okay. Okay. One day after tomorrow, please. Okay.
So I just wanted to ask a very practical question on behalf of the users.
Audience, yes.
So, I mean, at what resolution should you consider possibly refining your atomic model rather than doing rigid body fitting?
No,
I say consider because obviously you may try it.
Again, answer to that question is not easy to say. Yes, let's say that you have a perfect model, yes, and a perfect map, yes, and then you have your model is very good, yes. Then you can use at 10 angstrom, yes. But I wouldn't do that. If in practice you don't know that. If you see some blob like that, you don't know that what is in there. Yes. Why do people want their number? Okay. Let's say that 5 angstrom. Okay. Today 5 angstrom.
Today 5 angstroms. Yeah. I mean, I know you've published a study of a set of structures better than 4.5 angstroms, wasn't it? Yes. But I mean,
yes.
In-house, I guess you've looked at lower resolution.
Yeah, I think higher than 5 angstrom. That was like.
Was it 5? Okay.
Yeah, something like that. Yes, that was not because it is a optimal or there is a theoretical justification. That was because Alan Brown likes that number more than others. It is very difficult. You see that you have EM is not like crystallography. I've seen a 6 angstrom, and portions are 4.5 angstrom. You could do atomic model building there, yes. I have seen 3 angstrom, yes. Only some portions are at 4 angstrom, remaining are lower. Yes, it is very difficult to give a number. You just say do refinement, overfitting analysis, and say that you can or you may not do. Yes? Yeah. And at the end, whatever you do, you have to go back your observed maps. Yes. Mm-hmm. And see that if model describes the map, and if model is sensible enough to answer to the question, all this refinement and all other things, they are just the tools. Yes. So what we want is to answer some biological questions. If model is without me putting that answer to the model, yes, can answer to my questions, yes, then it was good. Yes. Mm-hmm. Otherwise, you have to do something else. Yes. Okay.